Okay, good morning or good day, everyone. So today we are going to discuss design methods, derivation of beam expressions, and strains in flexural members. So allow me to share my screen. Okay, so design methods, derivation of beam expressions, and strains in flexural members. So first, we are going to discuss the design methods, which involves the working stress design and as well as the ultimate strength design. So working stress design, also called as the allowable stress design or the straight line design. This was being used from the early 1900s up to the early 1960s. So here in this method, the dead load and live loads to be supported, which were called working loads or service loads, were first estimated, and then the members of the structure were proportioned so that stresses calculated by a transform area method did not exceed the uh, certain permissible or what we call the allowable values. On the other hand, the ultimate strength design is also called as strength design, was being used after way back 1963. So this method rapidly gained popularity because first, it makes use of a more rational approach than does the working stress design. Second, it uses a more realistic consideration of safety. And then lastly, it provides more economical designs. So ultimate strength design is widely used, especially in reinforced concrete design. However, the working stress design is very much applied when you are dealing with steel design. So as of now, we are using the ultimate strength design for designing reinforced concrete. Okay. So in this method, the working dead and live loads are multiplied, okay, by a certain load factors. These load factors refers to the safety factors, and the resulting values are called these factored loads. So the members are then selected, so they will theoretically just fail under the factored loads. So let's discuss derivation of some beam expressions. So here, in this figure, this is the nonlinear stress distribution at ultimate conditions, wherein we have here the strain variation, and then as well as the stress variation at ultimate load conditions. And then we have here the so-called beam section. And we have here the steel strain, which reaches or should be greater than or equal the yield strain. And here, in this portion here, this is referred to as the concrete strain. Okay, so when we say strain variation, tests of reinforced concrete beams confirm that strains vary in proportion to distances from the neutral axis, even on the tension sides and even near ultimate loads. Okay, so we have here the so-called neutral axis over here. Okay. And then when we say also stress variation, here the compression stresses vary approximately in a straight line until the maximum stress equals about 0.50 FC prime. Okay, so when the ultimate is reached, the compressive stresses vary from 0 at the neutral axis to a maximum value at or near the extreme fiber. So this is what we call the extreme fiber over here. So, in the derivation of beam expressions, there are some possible stress distribution shapes. So here, we have a typical beam section over here. And as you can see in this figure B, we have here the distance C serves as here as, let's say this is our neutral axis. And then we have here the FC prime. And then we have here the tension, which is equivalent to ASFY, which we have already discussed. This equation has been discussed in our previous topic. And then under this curve figure here has been converted into rectangular, wherein your FC prime would be now, this portion over here rather, would be 0.85 FC prime. And we have here the so-called portion over here considered as a distance A, which is equivalent to beta 1 times C. Okay, and again, we have here the tension, tensor force, which is equivalent to ASFY. So here, as you can see, we have the ACI 318-14, wherein you can again go to the internet, search for this one, ACI 318-14, and you may read this one online. We have here the following, same na siya, when we say ACI, this is where NSCP 2015 also was being sourced. So, na yung mga standards in the NSCP 2015 that came from ACI codes. So, if you happen to visit the web, just try to search this ACI 318-14, then you can read it online. So here, again, ACI is a code wherein it also deals with the English system, more on the English system. Unlike sa NSCP 2015, deals with the SI units. Okay, so under section 22.2.2.4.1 of the ACI 318-14 code, the concrete stress of 0.85 FC prime shall be assumed uniformly distributed over an equivalent compression zone bounded by the edges of the cross-section and aligned parallel to the neutral axis located at distance A. So this is what we call distance A. From the fiber of the maximum compressive strain as calculated by, so we have this specific equation to be considered when we are trying to get the value of our A, wherein A is equivalent to beta sub 1 times C. So in NSCP 2015, under section 422.2.2.4.1, concrete stress of 0.85 FC prime shall be assumed uniformly. So same lang yapon siya, no? O statement din sa ACI code, since we got NSCP 2015 standards from this ACI code also. Only that distance A, iya lang gi-represent as alpha, but same lang yapon na siya sa A. So again, same formula. Alpha is equivalent to beta sub 1 times C, or that is equivalent to A. So these are the basic formulas that we need to remember, especially when we are designing reinforced concrete. So it's important nga ato ni siyang ma-memorize. So again, sa ACI, more siya sa English system. And then in terms of units, and then NSCP 2015 is more on the SI units. So again, continuation. So again, let's discuss this distance C over here. So according to the ACI code, distance from the fiber of a maximum compressive strain to the neutral axis C shall be measured perpendicular to the neutral axis. So we have here the neutral axis, and here we have this perpendicular distance, so-called as C. So same lang yapon siya, no? as you can observe, same na siyang definition sa NSCP 2015. Again, mag-vary lang sila sa units. Okay? So we have here another important mga equations gyapon nga atong dapat i-consider or not only consider but also take time to memorize. Kay sometimes dili ni siya given sa board exam, especially sa board exam. So it's best that you would memorize these standards or these equivalent equations. So again, we have discussed about C and A. Now we'll discuss beta sub 1. So values here, as of ACI 318-14, values of beta sub 1 shall be in accordance with this table. Okay, so we have here the equivalent rectangular concrete stress distribution. Take note, the unit here of FC prime is in terms of PSI, wherein as again, I have said, ACI focuses more on English units. So if in this table, you can see that FC prime, if FC prime is greater than or equal 2,500 but less than or equal 4,000, the value of your beta 1 would be 0.85. And if it is greater than 4,000 or less than 8,000, use this equation, 0. For your beta 1, value for your beta 1, use this one, 0.85 minus 0.5 multiplied by FC prime minus 4,000 divided by 1,000. Or if FC prime is greater than or equal 8,000, the value of your beta 1 would be 0.65. So if you happen to get the value lesser than 0.65, you might as well check your solution. Otherwise, there's something wrong with the way with what your solution has, because it should not be less than 0.65. So here, under the NSCP 2015, which is more of the SI units. So here, FC prime is in terms of megapascal. And then here in this table, we have if FC prime is greater than or equal 17, but less than or equal 28, the value of your beta 1 would be 0.85. If your FC prime is greater than 28, but less than 55, then use this value, 0.85 multiplied by the product of 0.05 and FC prime minus 28 divided by 7. But if it is greater than 55, rather, use this value, 0.65. So take note, try to memorize these equations, especially when designing reinforced concrete. Okay, and also, dili po ni siya, sometimes di ni siya ginahatag ng mga formulas sa board exam. So better memorize this one. So we have already mentioned MN in our previous topic. So when we say M sub N, this refers to the theoretical or nominal resisting moment of a section. Then we have this equation, M sub U is less than or equal V M sub N, where your MU refers to the factored moment, which definitely is caused by the factor loads. And this is also considered as the required strength, ang MU, where your phi here represents the strength reduction factor. So if we multiply phi with Mn, this is considered as the usable flexural strength of the member, or often called as the design strength. So this is another formula that you have to memorize. So let's derive some formulas. Okay, so we have here the beam internal forces at ultimate conditions. So as you can see, our, again, I have discussed this one in our previous topic na, that to make it equilibrium, our tensile force should equate our compressive force. Okay. So again, we have here the distances C, A, and then we have this portion over here considered as 0.85 FC prime. And then we have here this distance D minus A over 2, wherein sa atong previous discussion, and we take moments here. Okay. So we have this equation. A is equivalent to ASFY divided by 0.85 FC prime P. So this could also be equal to rho FYD divided by 0.85 FC prime. But rho here has another value in this in the form of this equation. Rho is equivalent to AS over BD. So let's derive where this equation came from. So as what we call the to make or to have equilibrium, compressive force should be equal to your tension force or tensile force, wherein your C is equivalent to 0.85 FC prime AB, and your tension force is equivalent to ASFY. So if we are going to simplify this one and get the value of our A, this equation would now become A is equivalent to ASFY all over 0.85 FC prime B. So again, we could simplify this one further. So we can get the value of our AS here out of this equation here. So rho is equivalent to AS BD. So it would now become AS is equivalent to rho times BD. So that's why we have here this one, rho times BD. And then just copy Fy over here and then divide it by 0.85 FC prime B. So we can cancel out B in the numerator as well as in the denominator. So what remains would be rho Fy times D divided by 0.85 FC prime. So this is where this equation came from. So remember the derivation. So if ever you get lost with the formula, if you know how to derive, then there's no way na dili mo maka-formulate sa formula, maka-generate sa formula. Okay? But again, it's best if you will be able to memorize these formulas not directly. But if ever you got to forget, it's better that you know how to derive the formula. So another formula that we are going to consider would be this one. Phi M sub n is equivalent to phi multiplied by ASFY multiplied by D minus A all over 2. So ato na ni siyang na-discuss kani nga equation, may labot ng phi. So we take moments over here. Okay, so more like of a couple. And then this phi M sub n would be, remember katong equation, kani siya, less than or equal. So we'll make use of the equal sign. Okay, set aside sa atong less than. So we have here phi sub m is equivalent to m sub u, where your m sub u is equivalent to phi bd squared fy rho times 1 minus rho fy all over 1.7 fc prime. So your mn here is equivalent to t. So I As you can recall sa itong previous discussion, nata ani nga formula, m sub n is equivalent to t multiplied by d minus a all over 2. So, kani siya dinhi. Okay? Your tensile force is equivalent to ASFY, again, multiplied by d minus a over 2. So, if we add on phi, that would now be phi m sub n is equivalent to phi multiplied by ASFY times d minus a over 2. So, how do we get this formula? Kani siya. Kaning phi times m sub n equals to mu equals to phi bd squared fy rho times 1 minus rho fy all over 1.7 fc prime. So, we have known this equation naman, di ba, kaning a. We have derived that one earlier. A is equivalent to rho fyd all over 0.85 fc prime, where your rho here is equivalent to as all over bd. And then we have this equation also, phi m sub n is equivalent to phi asfy times d minus a over 2. So let's start with phi m sub n equals to m sub u is equivalent to phi, where your as is equivalent to rho times bd. So that's why we have here rho times bd, copy the fy, multiplied by d minus the value of your a, which is rho fyd all over 2 times this one, 0.85 fc prime. Okay? So if we simplify this one further, so of course, we'll take out the d's here. So this would now be placed outside, kaniatong d. So that's why we have here 1 na din siya dinhi. So again, phi times m sub n is equivalent to m sub u equals to this one, phi rho b. Then we have d, since ato manggipagawas ang d nganhi sa sulod. So d now times d would now become d squared fy times, this will now become 1 minus rho fyd, or fy rather na lang, kaya napagawas po na to ang d. So divided by 2 times 0.85 is equivalent to 1.7, and then you multiply it with fc prime. So this is where mo ni siyang derivation ani nga formula. Ani siya. Okay? So again, memorize this formula. Okay? So going back here in this strain stress diagram, so under the ACI code, strain in concrete and non-pre-stress reinforcement shall be assumed proportional to the distance from the neutral axis rather. So they are proportional. And then design assumptions for concrete. So the maximum strain at the extreme concrete compression fiber shall be assumed equal to 0.003. Okay? So that's the assumption based on the code. The maximum would be 0.003. So according to NSCP gihapon, same lang gihapon sila og definition since we got the NSCP 2015 from those codes such as the ACI code. So same, since this is unitless, so same gyapon ang ato ang maximum strain sa atong concrete compression, which is equivalent to 0.003. Okay? So again, going back, we have this formula man. We have known A is equivalent to ASFY all over 0.85 FC prime B, wherein your A is also equivalent to beta 1 times C. And if we are going to make use of this equation or simplify A equals to beta 1 times C, so the value of your C would also be equal now to A all over beta 1. So again, another formula to memorize, okay? So let's have a sample problem. We have here, determine the values of A, C, and tensile strain for the beam shown in the figure, where your Fy is equivalent to 414 megapascal and Fc prime is equal to 20.7 megapascal. So we have here the beam section. We have three 28 mm diameter bars. We have the base or the width equal to 355 mm, and then effective depth of 530 mm. And then we have here, we used here the assumption, katong 0.003, the maximum strain of concrete. And then we have here the tensile strain. So considering here, this is our distance C about the neutral axis, the perpendicular distance C about the neutral axis. And we have the effective depth, so which is D minus this one here, this distance would be the effective depth minus the value of your C, okay? So what we are asked is to get the value of A, C, and tensile strain. So how we do that? Again, we are going to make use of the formulas. So here, since these are proportional, okay, as you can see, so mag-ratio and proportion taani, wherein your strain sa tensile strain would be all over this one, D minus C, is equal to 0.003 all over C. So we have here this equation. So we all know that we have this equation C is equivalent to A all over beta 1. And then your A as another, we have the formula here for A, which is equivalent to ASFY all over 0.85 FC prime B, wherein we could solve or calculate the value of our AS, which is equivalent to pi over 4, the area of your reinforcement steel, pi over 4, which is 28 mm in diameter. Take the square, multiplied by how many bars? We have 3 bars here, so that's why we have 3 here. So the value of your AS is equivalent to 1,847.26 millimeters square. So we have here the given Fy equals to 414 megapascal. Fc prime is equivalent to 20.7 megapascal. And we have here the value of your base, which is equivalent to 355 mm. So if we are going to substitute these values over here, we could now get the value of our A, which is equivalent to 122.44 mm. Okay? So na-solve na natong A, pangitaon pa nato ang C, and as well as tensile strain. So C, again, we have this formula is equivalent to A all over beta 1. So again, going back sa katong value na to atong unsa gay ito gamiton, kung nganong 0.85 atong gamiton sa beta 1. So let's get back. So pila ta tong FC prime? FC prime is 20.7. So based sa atong earlier discussion, either the NSCP 2015, since we are using the SI unit, so less than or equal 28. So since our value sa atong given is 20.7 ang FC prime, so that's why the value of our beta 1 is equivalent to 0.85. Okay? So that's why we have here beta 1 equals to 0.85. So substitute the value of your A, which we have just solved, which is equal to 122.44, divided by beta 1, which is equal to 0.85. We have now solved the value of C, which is equal to 144.04 millimeters. So getting back to this equation, itong ratio and proportion, we could solve now the value of our tensile strain. So, unknown na to atong tensile strain. We have the value of our D, which is our effective depth, 530, minus our C, which is 144.04, equal to 0.003, divided by your C, which is again equal to 144.04 mm. So the value now of our tensile strain would be equivalent to 0.008038. So we have just solved what is asked on the problem, which are A, C, and tensile strain. Okay, so hope you understand our lesson. So if should you have any questions regarding this discussion, just feel free to message me. Okay, so that's all. Thank you everyone for listening.